Section 1.3, Radicals and Rational Exponents. Before we start talking about square roots, let's review perfect squares. A perfect square is any number that can be written as the product of an integer times itself. Below is a list of 15 perfect squares. And the way we got this list is we just evaluated 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth. So for example, 1, 4, and 9 are all examples of perfect squares, since 1 equals 1 squared, 4 equals 2 squared, 9 equals 3 squared. It is highly recommended that you memorize the first 15 perfect squares. It will make finding the square root of numbers and simplifying radicals later much easier if you have these values memorized. Now we'll talk about square roots and principal square roots. A square root of a is a real number that when multiplied by itself equals a. For example, negative 5 squared and 5 squared both equal 25. So 5 and negative 5 are both square roots of 25. In general, every positive number has two square roots, one that's positive and one that's negative. The principal square root of a is the non-negative square root. So out of the 5 and negative 5, which are both square roots of 25, 5 is the principal square root of 25 because it is a non-negative square root. Principal square roots are often written as radical expressions, with a symbol that we call the radical over the term we're taking the square root of, which we call the radicand. So this symbol here will read as root a, or radical a, or the principal square root of a, or even just for short, square root of a. Now we're going to evaluate each expression. When it comes to order of operations, the radical symbol both behaves as parentheses, where we want to evaluate what's inside the square roots first, and exponent at the same time, where after we simplify what's inside of the radical, we then take the principal square root of said number. So first, what's radical 25? Well, as we discussed before, we know that 5 squared is 25. 5 is non-negative, so radical 25 is positive 5. Next, what's radical 100? Well, from our table from earlier, we know that 10 squared is 100. So radical 100, or the principal square root of 100, is 10. Next, we're going to evaluate radical 16. First, we're going to start with the innermost radical. Since 4 squared is 16, then radical 16 is 4. Now we have to evaluate radical 4. Well, we know 2 squared is 4, so radical 4 is positive 2. Now we're going to evaluate the square root of 25 plus 144. Following our order of operations, we do first have to add what's inside of the square root. 25 plus 144 is 169. Since 13 squared equals 169, square root of 169 is 13. One thing to be careful of is the square root of 25 plus 144, not the same as the square root of 25 plus the square root of 144. Square root of 25 is 5, square root of 144 is 12, 5 plus 12 is 17. But as we've just evaluated, the square root of 25 plus 144 is 13. 13 is not the same as 17. So be very careful when taking the square root of the sum. The square root of the sum is not the same as the sum of the square roots, as we've just seen in this example here. Next, we'll do the square root of 49 minus the square root of 81. Evaluate the square roots first. Square root of 49 is 7, square root of 81 is 9, and 7 minus 9 is negative 2. One thing you have to be careful of is trying to take square roots of negative numbers. Keep in mind that for any real number x, when I multiply x with itself, I'm multiplying two numbers of the same sign, which means the product can never be negative. If x is 0, 0 times 0 is 0. But if x is negative or positive, well, positive times positive is positive, and negative times a negative is positive. So for that reason, x squared is always greater than or equal to 0. For this reason, the square root of a negative number is not a real number. There is a concept of taking the square root of a negative number, and we're going to see that later, but it will not be a real number. There's quite a few useful properties for evaluating square roots. In these properties, a and b are going to be non-negative numbers. The first property is the square root of a times b equals the square root of a times the square root of b. In other words, the square root of a product equals the product of the square roots. We also have a similar property for division. The square root of a over b equals the square root of a divided by the square root of b. The square root of a quotient equals the quotient of the square roots. And the third property is the square root of a to the 2k equals a to the k. The reason why this property is true is because a to the k squared, thanks to power to a power, equals a to the 2k. So the square root of a to the 2k would equal a to the k. These properties are very useful when it comes to simplifying expressions that involve radicals. In this example here, we're going to use the properties from the previous slide to simplify each expression, and we're going to assume all variables represent positive values. First, let's take a look at 600. 600 is not a perfect square, but there is a factor of 600 that is a perfect square. 600 is the same as 100 times 6. So thanks to the first property from the previous slide, square root of 600 is the same as the square root of 100 times the square root of 6. Since 100 is a perfect square, we can evaluate it. Square root of 100 is 10. Square root of 6 is not a perfect square, so we'll keep the square root of 6 as is. In order for the expression to be fully simplified, the value inside of the radical cannot contain any factors that are perfect squares. Well, if we think about 6, its only factors are 2 and 3. Neither 2 nor 3 are perfect squares. So square root of 6 is as simple as we can make it. So square root of 600 equals 10 root 6. In our next example, we want to simplify the square root of 162 times a to the 7th times b to the 8th times c squared. Starting off with the 162, we want to try to think of factors of 162 that are perfect squares. If you're not sure right away what those factors may be, one strategy is to factor the number in question into a product of primes. For example, 162 is the same as 2 times 81. From there, 81 we know is 9 times 9, which is 3 times 3. 162 is 2 times 3 to the 4th. So the square root of 162, a to the 7th, b to the 8th, c squared equals the square root of 2 times 3 to the 4th times a to the 7th times b to the 8th times c squared. From there, I'm going to rewrite each factor in the radical, so that way I can use the third property. 2 is just 2 to the first power. There's nothing I can do with that. Since 3 to the 4th has an even power, that's the same as 3 times 2 times 2. Now, for a to the 7th, 7 is an odd power. If we do 7 divided by 2, that equals 3 remainder 1. So a to the 7th, we can rewrite as a to the 2 times 3, 3 being the quotient of our division, times a to the first, and to the first because our remainder is 1. Now, 8 divided by 2 is 4, so b to the 8 can be rewritten as b to the 2 times 4, and c squared is the same as c to the 2 times 1. Now we're going to take the square root of the factors that we can. So the first factor we can take the square root of is the 3 squared, thanks to property 3 is 3 squared. Then the a to the 2 times 3, again, thanks to property 3, is a cubed. Next, the b to the 2 times 4, that's going to be b to the 4th, thanks to property 3. And lastly, c to the 2 times 1, which is c to the 1st, thanks to property 3. The values I could not take the square root of, which I did not circle, are going to stay inside of the radical. So I'm left with 2a inside of the square root when things are simplified a bit more. Then to finish up the problem, evaluate what we can. 3 squared is 9, a cubed, b to the 4th, c to the 1st stays c, and then the square root of 2a. And there's our answer, 9 times a cubed, b to the 4th c, square root of 2a. For the next problem, we're going to simplify 4 times the square root of 3 plus 2 square root of 27. When we add numbers involving radical expressions, it's a lot like collecting like terms. We want to make sure the radical expressions are exactly the same before we add the coefficients. Here, we have the square root of 3 and the square root of 27. They are not the same. So right now, 4 square root of 3 and 2 square root of 27 are not like terms. To try to make them like terms, we'll try to simplify each radical expression. 3 is prime. We can't do anything to simplify the square root of 3. 27, thinking of our multiplication facts, is 9 times 3, and 9 is a perfect square. So we can write the square root of 27 as the square root of 9 times the square root of 3. The root of 9 is 3, and now we can multiply 2 and the 3 that are in front of the radical. After simplifying the square root of 27, 4 root 3 plus 2 root 27 equals 4 root 3 plus 6 root 3. Since the root 3's are the same expression, we can collect our like terms by adding the coefficients. 4 plus 6 is 10, and we keep the root 3's behind them, as if we were doing 4x plus 6x. So 4 root 3 plus 2 root 27 is equal to 10 root 3. Next, we'll simplify the square root of 3 times the square root of 21. Square root of 3, as we stated before, is as simple as we can make it. 21, the only factors of 21 other than 1 and 21 are 3 and 7, neither of which are perfect squares. So both radicals on their own are already simplified. But we can still use property 1 to rewrite it in a more condensed form. Square root of 3 times the square root of 21, same as the square root of 3 times 21. 3 times 21 is 63. Now let's check to see if we can simplify. Well, 63, thinking about factors of 63 that are perfect squares, that was 9 times 7. So the square root of 63 is the same as the square root of 9 times the square root of 7. Square root of 9 is 3. Square root of 7 we can't simplify. The square root of 3 times the square root of 21 equals 3 root 7. Now for the last example, there's a few different ways we can approach this problem. If we look at 63 and 28 first, we know that 7 is a factor of both numbers. So to help make the number smaller, we're going to use the second property from the previous slide. And we'll rewrite the square root of 63 over the square root of 28 as the square root of 63 over 28. Now, since 7 is a factor of 63 and 28, when we reduce, we get 9 over 4. So the square root of 63 over the square root of 28 equals the square root of 9 over 4. Well, 9 and 4 are both perfect squares. So using property 2 again, the square root of 9 over 4 is the same as the square root of 9 over the square root of 4. The square root of 9 is 3. Square root of 4 is 2. So the square root of 63 over the square root of 28 equals 3 over 2. One thing that we like to see in simplified rational expressions is no radicals in the denominator of the expression. The process of rewriting an expression so that way there are no radicals in the denominator is called rationalizing the denominator. Now, sometimes our denominators are going to be the sums and differences involving radicals that we can't simplify any farther. To help rationalize, we're going to use something called conjugates. Conjugates are expressions where the terms are the same, but the sign in the middle is opposite. So for example, if we have the expression a root b plus c root d, its conjugate is a root b minus c root d. Notice how both expressions involve a root b and c root d. The difference between them is the sign in the middle, 1 plus 1 minus. We're now going to simplify and rationalize the denominator of each expression. We're going to assume all variables represent positive numbers. First, let's take a look at the square root of 6 over y to the fifth. Using our properties from the previous slide, we can rewrite our expression as the square root of 6 over the square root of y to the fifth. 5 divided by 2, we get 2 with a remainder of 1. So the y to the fifth, we can write as y to the 2 times 2 times y. Thanks to our third property, we can take the square root of the y to the 2 times 2. When we do, the square root of y to the 2 times 2 would just be y squared. The other y, which we can't take the square root of, stays in the radical. The square root of 6 we cannot simplify. Now we're going to rationalize our denominator. In these types of problems, the way we can rationalize our denominator is by multiplying the bottom of our fraction and the top of our fraction by the radical expression. So our radical expression in the denominator is the square root of y, so we're going to multiply top and bottom by the square root of y. The reason why we want to do that is if we multiply the square root of a number by itself, by the definition, it should just equal that number. So the square root of a squared equals a. In the numerator, square root of 6 times square root of y is the square root of 6y. In the denominator, the square root of y times the square root of y is y, and we still have that y squared in front that we have to multiply by. When we multiply the y's in our denominator, y squared times y is y cubed. So the square root of 6 over y to the fifth, after being simplified and our denominator is rationalized, equals square root of 6y over y cubed. In the next problem, we're going to simplify and rationalize the denominator of the square root of 3x to the fifth all over 5y. Similar to what we did in the previous problem, we're going to rewrite our expression as the square root of 3x to the fifth over square root of 5y. The x to the fifth we can simplify in the exact same way we did with the y to the fifth in the previous problem. The square root of 3x to the fifth would simplify to x squared times the square root of 3x. In our denominator, we cannot simplify any farther. Now with all of our radicals simplified, let's go ahead and rationalize our denominator. We'll do so here by multiplying top and bottom by the square root of 5y. Square root of 5y times the square root of 5y is 5y. In the numerator, multiply the values inside of the radicals. 3x times 5y is 15xy. 15 cannot be simplified any farther, and x and y are not perfect squares themselves. So the square root of 3x to the fifth over 5y, after being simplified and rationalized, is x squared times square root of 15xy all over 5y. In our next example, we're going to see how conjugates can be used to rationalize the denominator. We want to simplify and rationalize 2 over 4 plus root 3. The difference between this example and the other two is our denominator is something plus root 3. So I can't just multiply top and bottom by root 3 because I would have to distribute the root 3 in, and I would have 4 root 3 plus 3. I'm still stuck with the radical in the denominator. But if I multiply top and bottom by the conjugate, now the conjugate of 4 plus root 3 is 4 minus root 3. What makes conjugates so powerful here is the fact that we're using one of the special product rules. The special product rule is a plus b times a minus b is equal to a squared minus b squared. So if we FOIL out the denominator or use the formula above, we get 4 squared minus root 3 squared. In the numerator, we'll distribute 2 times 4 is 8, and 2 times root 3 is just 2 root 3. Remember not to multiply numbers that are not in radicals with numbers that are in the radical. So 2 times the square root of 3 is not the same as the square root of 6. We would have to keep it as 2 times the square root of 3 because the 2 is not inside of square root. Minus 2 root 3 we cannot simplify any farther, but in our denominator 4 squared is 16, square root of 3 squared is 3, and 16 minus 3 is 13. So 2 over 4 plus root 3 is equal to 8 minus 2 root 3 over 13 after we rationalize the denominator. In the next example, we're going to simplify 4 over square root of 3 minus square root of 7. Just like before, we're going to use conjugates since our denominator is a sum or a difference involving the radicals expressions. The conjugate of the square root of 3 minus square root of 7 is the square root of 3 plus the square root of 7, and we're going to multiply the numerator and denominator by the square root of 3 plus the square root of 7. In the numerator, we can distribute in the 4 square root of 3 plus 4 square root of 7. In the denominator, we get root 3 squared minus root 7 squared after using our special product rule. We can't simplify the numerator any farther, but in the denominator, we get negative 4. Now we can simplify this even farther. Negative 4 does divide both 4 root 3 and it divides 4 root 7. One thing to keep in mind, if you're going to divide two terms of an expression by a number, you have to divide each term by that number. So 4 root 3 divided by negative 4 is negative root 3. 4 root 7 divided by negative 4 is negative root 7. So 4 over root 3 minus root 7 is negative root 3 minus root 7. Now we're going to generalize the idea of square roots to what we call nth roots. And we're also going to talk about principal nth roots. An nth root of a is a number that when multiplied by itself n times equals a. If a has at least one nth root, then the principal nth root of a, written as the nth root of a, is the nth root with the same sign as a. Now, the value of n, which we have on the little hook of the radical, we call the index of the radical. Now, when it comes to square roots are what we would call second roots. We assume the index is 2, but because we work with square roots so often, we don't write the 2. It's just assumed to be there. So the index of all square roots is 2. What's great about nth roots is they have the same properties that we've seen in square roots. So if the nth root of a and the nth root of b are real numbers, the nth root of a product is still the product of the nth roots. The nth root of a quotient is the quotient of the nth roots. The only difference is when we take the nth root of a to the k times n, that is going to equal a to the k. It's exactly the same as what we've seen with square roots if we replace the n with 2. So all the properties of square roots can be easily extended to nth roots. Now we're going to simplify and rationalize the denominator of each of these expressions. First, let's start off with the cube root of negative 27. When it comes to cube roots, fourth roots, and fifth roots, it does help to factor the number into a product of primes. So 27 is 3 times 9, and 9 is 3 times 3. So 27 is 3 cubed. Since 3 is odd, we can take the odd root of a negative number. The reason being is if I multiply an odd number of negatives together, that product is negative. So I can find a negative number multiplied to itself 3 times. I'm going to get negative 27. Since I know 27 equals 3 to the third, if we take negative 3 and raise it to the third, because 3 is odd, we get negative 27. So negative 27 has at least one cube root, specifically negative 3. And since negative 3 has the same sign as negative 27, our principal cube root of negative 27 is negative 3. Next up, the fourth root of 16. 16 is 4 times 4, and 4 we know is 2 times 2. So 16 is equal to 2 to the fourth. Since we're trying to take the fourth root of positive 16, we know 2 is a fourth root of 16 and is positive, then the principal fourth root of 16 is positive 2. Now we're going to simplify negative 5 times the fifth root of 6,250 x to the 23. Now, just like before, we're going to try to rewrite the 6,250 as a product of primes. 6,250, 625 times 10, 625 is 25 times 25, 10 is 5 times 2, and the 25s are each 5 times 5. So 6,250 is equal to 2 times 5 to the fifth power. Now for x to the 23, I want to try to use the third property that we saw in the previous slide. Since 23 divided by 5 is 4 remainder 3, then x to the 23 is the same as x to the 5 times 4 times x cubed. So rewriting our expression, we have negative 5 times the fifth root of 2 times 5 to the fifth times x 5 times 4 times x cubed. Similar to what we did in the square roots, we're going to take the fifth root of whatever we're writing as a power of 5. Well, 2 is not a power of 5, 5 to the fifth is a power of 5, and the fifth root of 5 to the 5, thanks to its third property, is 5. We can apply the third property to x to the 5 times 4, and we get x to the 4. And unfortunately, we can't apply the property to x cubed. What's left in our fifth root? Well, it's whatever we didn't circle, which is 2 times x cubed. Now we can simplify what's outside of our fifth root. Negative 5 times 5 is negative 25. X to the fourth times the fifth root of 2x cubed. For the next example, we're going to simplify the fourth root of 81a to the 40th over 625b to the 24th. If we rewrite our expression using the second property, this is equal to the fourth root of 81 times a to the 40th over the fourth root of 625b to the 24th. Now, using the same strategy we did in the previous problem, we can rewrite 81 as 3 to the fourth, a to the 40th as a to the 4 times 10, our 625 as 5 to the fourth, and our b to the 24th as b to the 4 times 6. Now take the fourth root of what we can. The fourth root of 3 to the fourth is 3. The fourth root of a to the 4 times 10 is a to the 10, thanks to the third property. The fourth root of 5 to the fourth is 5. Fourth root of b to the 4 times 6 is b to the 6, thanks to the third property. Our expression simplifies to 3a to the 10th over 5b to the 6th. Now we're going to simplify 9 over the cube root of 81x. First, we do want to simplify our cube root. Now, 81 is the same as 3 to the fourth. Now, one thing to be careful of is that we are taking the third root, not the fourth root. So we need to rewrite the 3 to the fourth, so that way we have something being cubed. Well, doing the same thing we did with the variables, if we do 4 divided by 3, that's 1 with a remainder of 1. So 3 to the fourth is the same as 3 to the 3 times 1 times 3 to the first, and we still have the x there. Now, the only thing we can take the cube root of is the 3 to the 3 times 1, and when we do, we get 9 over, well, the cube root of 3 to the 3 times 1 is 3. The 3x, which we don't have circled, stays inside of the cube root. Now we need to rationalize the denominator. Now, what's different here is we're dealing with a cube root. If I try multiplying top and bottom by the cube root of 3x, the same expression I have in the denominator, the problem is I'm going to get the cube root of 9x squared. 9 and x squared are not perfect cubes, so I wouldn't be able to simplify. So instead of just multiplying by the cube root of 3x, I'm going to multiply top and bottom by 2 of them. So I'm going to multiply top and bottom by the cube root of 3x quantity squared. In the denominator, cube root of 3x times the cube root of 3x squared is the cube root of 3x cubed. Now in the numerator, as an extension of property 1, the cube root of 3x squared is the same as the cube root of 3x times the cube root of 3x, which is the same as saying the cube root of 3x times 3x. 3x times 3x is 9x squared. So I have 9 times the cube root of 9x squared all over 3 times the cube root of 3x cubed. Well, the cube root of 3x cubed is just going to be 3x. Not much to simplify in the numerator. And 3 times 3 is 9, which is going to cancel with the 9 in the numerator. So at the end, we have the cube root of 9x squared all over x. Now we're going to discuss rational exponents. When exponents were originally defined, if we were to evaluate a to the n, where n was a positive integer, a to the n represented multiplying a to itself n times. Later, we defined a to the 0 to equal 1 as long as a itself was not 0. We also defined negative exponents. If we had a to the negative n, that was the same as 1 over a to the n. So this allowed us to evaluate a to the n for any integer exponent. But now we're going to take a look at rational exponents, where rational exponents are exponents that are fractions. The way we define rational exponents is based off of principal roots. So if we write a to the m over n, where m over n is the rational exponent, that is the same as the nth root of a to the m, where the denominator of our exponent is the index of the radical. Well, instead of having m inside the radical, we can also put it outside and write the nth root of a all raised to the nth power. So again, a to the m over n equals the nth root of a to the m, which equals the nth root of a all raised to the nth power. Keep in mind the denominator of the exponent is the index of the radical. Now we're going to express each expression in exponential form. Right now we see both of these expressions with radicals. We're going to rewrite them where instead of radicals, we have exponents. If we take a look at first, the square root of c, recall that when we don't have an index explicitly written for the radical, we assume that is index 2. We also don't see a power on c, so we can assume that's c to the first. Using the definition of rational exponents we saw in the previous slide, the square root of c is the same as c raised to the 1/2 power, and that would be the exponential form. Next, for the fourth root of x cubed, we would have x raised to a rational power. Now, what would be the denominator of the rational power? Well, the index of our radical is 4. 4 would be the denominator of our exponent, and our numerator would be the power that 3 is currently being risen to, which is 3. So the fourth root of x cubed is the same as x raised to the 3/4. Now we're going to simplify each of the following expressions. Notice how all of our expressions involve rational exponents. And at this point, we may not be comfortable with rational exponents. So our strategy for evaluating them is to rewrite our rational exponents as radicals. We'll start off with 625 raised to the 1/3. If we were to write it in radical form, the 3 would be the index of our radical because 3 is the denominator of our exponent. Inside would go the 625. Now, as for the numerator, which is 1, anything to the first power is itself. We could either raise 625 to the first power, which would still be easy to do, or we can put the 1 outside, which is also still really easy to work with. As we evaluate, as we stated before, anything to the first power is itself. So we have the cube root of 625. If we were to rewrite 625 as a product of primes, the cube root of 625 is 5 to the 4th power. Now, what's really nice about rational exponents is it can make it very easy for us to simplify rational expressions. If I put the cube root of 5 to the 4th back into rational exponent form, that'd be the same as 5 to the 4/3. But 4/3 is an improper fraction. 4/3 we know is the same as 1 plus 1/3. So 5 to the 4/3 is the same as 5 to the 1st times 5 to the 1/3, thanks to our exponent properties. 5 to the 1st is just 5. Because we do want our expression back in radical form, because that's easier for most people to understand, 5 to the 1/3 is the cube root of 5. And there we have 625 to the 1/3 equals 5 cube root of 5. And notice how we went back and forth between radical and exponential form to help us simplify. You don't necessarily have to simplify the radical the way we did here by putting it back in rational form. You could do it just like we did in the previous exercises, but this is just a little tip that if you want to use this to help simplify, you can. Now we're going to take a look at two examples at once. Notice how we have negative 25 to the 1/2 and the quantity negative 25 to the 1/2. Both expressions look very similar. The difference is the parentheses, and the parentheses are very important for how we set things up and evaluate. For the first example in the bottom left, there's no parentheses around the negative 25 to the 1/2. So the 1/2 only affects to 25. So when I rewrite negative 25 to the 1/2 in radical form, the negative, which is not affected by the 1/2 power, stays outside. And because it's a 1/2 power, the denominator being 2, our index is 2, which means we do not have to write an index on our radical. So negative 25 to the 1/2 without parentheses is equal to the negative square root of 25, which equals negative 5. On the other hand, in the second example, the negative 25 to the 1/2, where there's parentheses, because we have the parentheses, negative 25 goes inside of the radical, because negative 25 is the base to the 1/2 power in this example, whereas in the previous example, only 25 was the base, not the negative. But here we're trying to take the square root of a negative number, and as we discussed before, we cannot take the square root of a negative number. So negative 25 to the 1/2 power is not a real number. Now the last example is one where there's several different approaches to go about it. We could write it right now in radical form. The problem is we can't really do anything about the fourth root of 25 right away. And I really don't want to cube 25. That's a really big number to cube. And we do have the negative power, so we would have to flip as well. We know 25 is a perfect square. So one strategy we can use is we can rewrite the 25 as 5 squared. So 25 to the negative 3/4 equals 5 squared to the negative 3/4. Now from there, we can use the power to a power rule. The power to a power rule states if we have a to the m raised to the n, that equals a to the m times n. So if I have a power to a power, I can multiply the powers. This property also holds true for rational exponents. So to simplify, the 5 squared to the negative 3/4, using my power to a power, that's 5 to the 2 times negative 3/4. Now multiply, 2 times negative 3/4 is negative 3/2. And you can see I just drove down what the index of my radical would be into a much smaller number. Now we can use the fact that our exponent is negative. Our property for negative exponents is the same as what we've seen in the past for integers. So 5 to the negative 3/2 equals 1 over 5 to the 3/2. If we were to simplify, because 3/2 is an improper fraction, 3/2 is the same as 1 plus 1/2. So 5 to the 3/2 is the same as 5 to the first times 5 to the 1/2. And we get 1 over 5. 5 to the 1/2 is the square root of 5. Remember, we don't like radicals in the denominator, so we'll rationalize, multiplying top and bottom by square root of 5. And we get the square root of 5 over 5 times, well, square root of 5 times square root of 5 is 5. And when we multiply the 5 and the 5, we get square root of 5 over 25. So our 25 to the negative 3/4 equals the square root of 5 over 25.